Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome, thanks for coming. It's with great pleasure that I will introduce Dr. Daniel Sheehan. He originally got his undergrad degree in chemistry from, where is it? What's that?
Santa Clara.
Santa Clara, sorry. And then his PhD in physics from UC Irvine. And now he's been teaching at the University of San Diego, where he was my undergrad advisor, not only in some of this research, which I worked on him with, but also in zero gravity research on the Vomit Comet. So he's been a very good mentor to me. And he's going to be presenting Batteries Not Included, Perpetual Computing with Perfect Cooling, which is really going to challenge a lot of the fundamental ideas that we have, and also challenge us to remember what we went through in our undergrad physics classes. So without further ado, Dr. Daniel Sheehan.
Thank you, Andrew. Okay, this afternoon I would like to introduce you to some ideas that have been percolating and developing over the last 20 years, which I think would have some significant impact both on the electronics industry, but on energy production in the world as a whole. And before I start, I'd like to, first of all, acknowledge some of my collaborators recently, in particular Andrew, whom I worked with about 10 years ago, and we stayed in contact over the years. And I'd also like to ask you to ask questions, because a lot of what I'm going to say will offend you, I think, okay, in terms of what you learned in thermodynamics. But what thermodynamics tells everybody, and one of its central messages is, all things change, including maybe thermodynamics itself. So the outline of this talk will first talk about heat generation and ideal power in the electronics industry, and then review thermodynamics and the status of the second law, and then discuss some experiments which have been in the works for about 10 years, and both in theory, experimental, and planned experiments, and possible applications that these might have. Now, heat generation in electronics is usually considered bad, except if you're making a toaster. In general, something like a chip, for every 10 degrees change in a chip's temperature will result in roughly a factor of 2 degradation in its lifetime. There's a tremendous amount of energy put into electronic devices, both in terms of energy to make it operate, but also to cool it. And this increases design complexity and reduces the reliability of electronic devices and customer acceptance. The cooling fans on a computer, for instance, are obnoxious, and in general, the hot laptop has actually developed a syndrome. I think it's called the toasted leg syndrome, I think, in the medical community. And most of this stems from Moore's law, ultimately. The thermal design power of a device is basically its capacitive energy, 1/2 CV squared times the clock rate of the device. This is a plot of the power density in watts per square centimeter versus years. This is actually an Intel slide, which shows the power density of Intel chips starting back in the 1970s and continuing into this millennium. And Intel itself recognizes that as time goes on, the power densities have achieved hot plate temperatures and will eventually approach nuclear reactors, rocket nozzles, and the surface temperature of the sun if things continue, because of the capacitance of the system's capacitive energy and the higher clock rates. The solutions that have been proposed, lower power elements, undervolting, underclocking, more of everything else, fans, radiators, heat sinks. But another possibility is to consider new power sources. So I'd like to ask you to think, what would you consider to be an ideal power source? If you were just dreaming, what would be the ideal power source? You'd want it to have as high a power density and energy density as possible. You want it to be integrable into your technology, inexpensive, ubiquitous, non-polluting, renewable, and even recyclable. And now that seems almost impossible. Now, if you look at thermal energy, it has some of these attributes. If one calculates the thermal energy in the ocean, the atmosphere and crust of the Earth, there's roughly 10,000 times more energy in thermal energy than there is in all the fossil fuel reserves, all the oil, gas, coal, and everything else. It's constantly replenished by solar power and by radioactivity in the crust. And to put this in perspective, if you have a glass of soda or a can of soda here, the amount of thermal energy in a can of soda, just the heat energy alone, is equivalent to the chemical energy of about 1/10 of a kilogram of TNT. And that applies not just to the soda, but it applies to the chair, to the air, to your pants, to your glasses, to the chip itself. Everything is loaded with energy. The air in this room is moving roughly sonically. The RMS speed is about 400 meters a second, which is the speed of sound. Everything is thermal in the end. And if you recognize that, you can see that we live in a reservoir of tremendous amounts of energy, but we consider it unusable. And we instead decide we're going to buy energy at tremendous cost, not just to our pocketbooks, but to the ecology of the planet and everything else. So heat has a number of characteristics which you would consider to be ideal. First of all, it's ubiquitous and it's basically inexpensive. It's free, it's everywhere. It has very high energy densities. The energy density of all the chairs in this room is equivalent to several boxes of TNT, literally. It is non-polluting by definition. It's everywhere and keeps us warm. But there are thermodynamic constraints associated with this. Most energy most work derived from heat comes at the expense, only when you have large temperature gradients, things like heat engines. Also, it's not considered renewable or recyclable yet, and to achieve high power densities and so on, have thermodynamic constraints. But that basically boils down to this law of physics. Now, there are 4 laws of thermodynamics. How many of you have studied thermodynamics sometime in your career? Okay, good. So you probably get chills when you see this, and not good ones either. There are 4 laws. The 0th and 3rd law are basically definitional. The 0th law says you can make thermometers. You can define equilibrium. The 3rd law can be stated in various ways, but primarily it has to do with fiduciary entropies. The 1st and 2nd law are the heart and soul of thermodynamics. They're the flesh and bones of it. The other ones are basically throwaways in comparison. The 2nd law has lots of different statements. The Kelvin-Planck form, you can read the fine print, but basically it says you can't turn heat into work solely. That's not possible. The Clausius form says heat goes from hot to cold, and perpetual motion machines of the 2nd type are impossible. There are 3 kinds of perpetual motion machines, the 1st, 2nd, and 3rd type, depending on which law of thermodynamics they purportedly violate. Perpetual motion machines of the 3rd type are already known. Superconducting currents are ones which flow forever and never run down, so the 3rd law can be broken, at least in terms of perpetual motion machines. Additional statements: refrigerators, no perfect refrigerators or heat engines. All natural processes are irreversible. Entropy change for any spontaneous process is always greater than or equal to 0. In the book that Capek and I wrote about 5 years ago, listed down here, we actually found about 21 different formulations of the 2nd law alone, and we didn't even stop counting. We just decided we ran out of pages to devote to the subject. But this kind of reminds me of a quote from Truesdell, who was a great historian of science, and he said, "Every physicist knows exactly what the 1st and 2nd law are. The only problem is no 2 physicists agree on what they are." Okay? But whatever the 2nd law is, people assume that it's absolute. Now, in a sense, we feel that the 2nd law is true because of all the colloquial statements about it, that we live our lives through the 2nd law. Even time itself moves forward, purportedly because of the 2nd law. Even down to the most jaded and extreme, Murphy's laws. If anything can go wrong, it will, and its corollaries like situations tend to progress from bad to worse. Why? Because it's more likely for things to go bad than to go well. And in the end, we're all going to die. Okay, that's the ultimate statement. Heat death of the universe and of ourselves. We will be claimed by the 2nd law. The 2nd law has built around it a mystique by the scientific community. This is perhaps the most famous of all the quotes by Arthur Eddington, who was on the par with Einstein in the early 20th century. The law that entropy increases, the 2nd law of thermodynamics, holds a supreme position among the laws of physics. And if any of your theories go against the 2nd law, I can give you no hope but to collapse in deepest humiliation. This is not a scientific statement. It's a statement of religion or belief. But this is what scientists who actually decide to challenge the 2nd law must face. But this neglects the epistemological nature of laws of nature. Physical laws are observations about the world. They're experimental and not theoretical. Many people think the laws are somehow discovered and proved. You don't prove physical laws, you simply verify them. And this really boils down to, in some sense, Hume's law problem with induction, which you took philosophy know that if you do something a number of times, that does not mean the next time you do it, it will be the same. So for instance, I can flip a dollar 100 times and get 100 heads out of it. That doesn't mean I'll get a head on the 101st try. And that's true in science as well. You can make measurements again and again, but that doesn't mean you will always get the same result when you go into new regimes, particularly with new technologies and new physical regimes. Now, as an example, let's look at the first law, conservation of energy. In 1800, 200 years ago, there were basically only two kinds of energy which were recognized, kinetic and potential, like gravitational potential energy and kinetic energy. By 1850, it had been discovered or realized that heat itself is just a form of kinetic energy when it comes to things like gas molecules. And so they added a new kind of energy and developed thermodynamics as a result. 1905, rest mass energy gets discovered, and even conservation of energy is no longer even true in word. It's conservation of mass energy. 1913, zero-point energy, energy in the vacuum, false vacuum energy, which is used to explain perhaps the existence of the universe itself. 1998, those of you who have been keeping up with cosmology know that the universe is expanding at an accelerating pace. This is purported to be caused by a new type of energy, dark energy, whose nature is completely unknown. So in a sense, the first law is something that's always been patched up. It's always been revised. It does not have a finite form, and in a sense, it's not even a law. It's an accounting system. Whenever you find a new kind of energy in the world, something that causes change, you simply chalk it up a new kind of energy, and you've patched up the first law. But not so with the second. The second law says something very particular, and it cannot, in a sense, squirrel out of its difficulties. It was first proposed nearly 200 years ago, about 185 years ago, by Carnot discussing heat engine efficiency, and formal definition started in about 1850. All the luminaries of 19th century physics, from Maxwell, Boltzmann, and Gibbs, and Planck, all contributed to the second law and its mystique. In fact, Max Planck created, in a sense, started quantum mechanics in 1900 with the description of black body radiation. That is actually a thermodynamic problem. So thermodynamics, in a sense, segued into quantum mechanics. And by 1910, for all practical purposes, all statements of the second law were completed, a century ago. And you would be hard-pressed to find any law that we know now which has not undergone some sort of revision or rethinking over that 100 years, except perhaps for the second law. And in thinking about it, I came up with this graph, which takes a little bit of explanation. During the last century, the 20th century, there were three major paradigm shifts: relativity, quantum mechanics, and chaos theory. And if one examines the parameter space that was understood 100 years ago, let's say in 1910, before any of these had really caught hold, one would find the following. If one plots on this log scale the temperature, which is basically a proxy for energy in systems, and the log of the scale length of systems, one would find that in 1910, our understanding of the world was basically bounded on the bottom end by the size of cells, what we could see with optical microscopes, and the size of nearby stars, maybe 1,000 light years, something like that. The temperature scales were down to about liquid helium temperatures, and at the high end, high temperature arcs, several million degrees. And that's about it. 100 years later on this log scale, we have now pushed things out down to maybe about 10 nanokelvin, down to Bose-Einstein condensates in temperature. So we've gone down almost 10 orders of magnitude here. And in the high temperature regime, the Large Hadron Collider will create temperatures on the order of about 10 to the 16th Kelvin, which is on 10 orders of magnitude higher in temperature. Our universe has expanded in our understanding of it, and now we understand it over a factor of a million greater size when we discover galaxies and galactic clusters and the overall large-scale structure of the universe. And on the small scale, we have been able to investigate things as small as quarks and smaller, or I should say down to quarks, about 10 to the minus 18 meters or so. So we have expanded our parameter space enormously, and in doing so, we have actually had two revolutions spurred by this, or helped along by these. Relativity looks at high energy and large scale sizes of the universe for general relativity and special relativity high energies. And quantum mechanics, where one has very small objects or things that are very cold, in which their wave-like properties become apparent. So paradigm shifts in the 20th century have actually been stimulated by our increased technology and our ability to see different scales and energy and size. And this is a log scale. So to put this in perspective, when the second law was set in stone, the area of this compared to the area of this is comparable to a speck of dust in the center of this room. And we would expect then, Well, okay, it might be true in that speck of dust region, but should it be true in the entire room? Yeah?
I'm surprised you include chaos theory as one of the three given the importance of relativity in quantum mechanics.
Well, that's emerged in the last 30 years. Some people consider it a paradigm shift, and in chaos theory, the idea behind that is that although the laws of nature may be deterministic, that doesn't mean we can predict things, because small changes in initial conditions tend to make things unpredictable. So it's undermined the classical paradigm that we can predict the future easily. So I would consider it a somewhat of a change in mindset, but that's a personal taste. Okay, you wouldn't, I guess. Okay, it's fine.
I'm the expert, so I'll defer to you.
Okay, so what I find more interesting is this. To have this speck of dust, the parameter space that we understood when the second law was set in stone, and to believe the second law was true there, and then to presume that it should be true over the parameter space, which is many orders of magnitude greater, is kind of presumptuous. And not only presumptuous, but it's surprising. What's more surprising to me, that challenges to the second law are so sparse and have been so mishandled over the last 100 years. It's more surprising to me that the second law hasn't been broken yet, I think. It's probably far more surprising. Now, in the last 20 years, there's been a revolution in the discussion of the second law. These are various groups around the world listed by the lead in the group and various institutions and country. The number of researchers in the group and the number of referee publications in mainstream referee journals in physics and chemistry, and whether these are experimentally testable or not. And this list is interesting in the sense that there are now in the mainstream literature more than 25 different challenges, theoretical challenges, some of which are in principle theoretically testable, that challenge the second law, in over 70 refereed journals, many of which are top flight journals in the physical literature. You'll recognize Physical Review Letters and Physical Review and so on. But if you look at the last 15 years, there have been 10 times more publications challenging the second law in the last 15 years than in the previous 150 years combined, which means that the publication rate in challenges has increased a factor of 100 in the last 15 years. And those of you who understand, let's say, the structure of scientific revolution, the Kuhnian work, realize that when you see this pattern that often prefaces a paradigm shift of some sort.
And sometimes doesn't.
Sometimes doesn't. I said sometimes. Okay. So my desire is to see whether there is or not. I'll be the first to say that the second law is absolute. It's absolute until it is no longer absolute. And at the University of San Diego, we've investigated a number of them over the last 20 years. My background originally was in chemistry and plasma physics, so the original ones were posed in the plasma area and in chemistry. Gravitating ones have also been proposed, ones in solid state. The ones with stars indicate ones in which laboratory experiments have been conducted corroborating the central processes invoked in the challenges. And these are other researchers in the field who have done work which have corroborated some of the theory behind the USD challenges. What I'd like to talk about primarily today is a series of challenges which deal with solid-state devices. And here are a few references for some of the original articles in the area. And the ideas behind this are prefaced on the idea of PN diodes. How many of you have enough solid-state physics to have worked with PN diodes? Okay? Okay, good. All right, let's take a look, for those of you who haven't. Okay, PN diode. In the simplest form, you basically take a piece of silicon and dope one side and another with different materials. N-type doping would correspond to something like phosphorus, which has one extra electron in the valence shell, which it can donate to the lattice, which increases the number of electrons in the lattice that are freely mobile. In the P-type silicon, this would correspond to a small amount of doping, maybe 1 part in 10,000 or a million or something like boron, which has one fewer electrons in its valence shell, which can receive an electron from a silicon, creating a positive hole, and that hole this positive hole can move around the lattice by the transfer of an electron. And as a result, you have an excess of holes on this side and an excess of electrons on this side. Because of the difference in concentrations of mobile electrons and mobile holes, the electrons naturally diffuse to this side into the P region, and holes will naturally diffuse into the N region. This diffusion continues until the until the chemical potential is balanced by an electrostatic potential. In other words, a buildup of positive charges here, negative charges here. This creates a built-in potential, which is given by this, kT, thermal energy over the charge, logarithm of the acceptor and donor concentrations, those are the dopants, over the intrinsic density of silicon. And this voltage would typically be on the order of a volt or less. And over the distance over which this would occur would be called the depletion region. The electric field in the depletion region, electric fields are defined as voltages divided by distances, change in voltage over change in distance. And because it's about a volt, but maybe over a distance of the order of a micron or less, the electric fields can be very intense. Now, let's change this just a little bit. We're going to take the p-in diode and we're going to bend it into a horseshoe shape. So the N region is bent around here, and there's a vacuum gap left between the P region and the N region. Again, where the two are joined, one has the depletion region and one has a voltage drop across there. But now one has a vacuum gap here. Now, based on Faraday's law, in the time-independent form of Faraday's law, or if you wish you want to use conservation of energy, you can show the following. If you take a charge and move it through a potential drop, let's say, across the depletion region, then if you bring it back around a closed loop, it has to come back to its original potential in the end, which means that if there's a potential drop here, there has to be a potential drop somewhere else in this circuit. That's required by Faraday's law or conservation of energy, if you wish. There's not going to be a potential drop in the bulk of this material, because if there were, that would result in an electric field which would drive a current, which is presumed not to exist because this is an equilibrium system, which means that the voltage drop has to occur across this vacuum gap. If there's a voltage drop across this vacuum gap, that means there's an electric field, and the electric field would be the built-in voltage over the vacuum gap. But now if you have an electric field in this region, you have stored electrostatic energy in that field, which basically makes this a capacitor. This is a thermally generated capacitor, one without a battery, and one which will retain its electric field until it is either discharged or this piece of silicon disintegrates. So basically it's what I would call a thermal capacitor. The pressure holding these plates, pulling these plates together is the electrostatic stress, which is given by the permittivity of free space divided by 2 times the electric field squared. Now you'll notice that whereas the depletion region might be a micron wide, the width of the gap here is arbitrary. If you make this very narrow, the electric field can be very large, much larger than across the depletion region. And since the pressure and energy density scale is E squared quadratically, the energy in this region here can be 2 or 3 times, the electrostatic energy here can be 2 or 3 times that over here. So one has a thermal capacitor. Now, once we proposed this theoretically, we decided, well, we should probably model this numerically. What we did was, Andrew actually did this work about 10 years ago. We took the top-end semiconductor device simulation codes by Silvaco, the Atlas codes, and simulated these. Basically just built these structures, leaving a vacuum gap here. And indeed, the electric field was of the same magnitude and the location that we predicted. And one can create 2 different forms of this, where the vacuum gap is open and where the vacuum gap is closed. This would be a high energy configuration of the system based on the capacitive energy. Whereas if you close it, the energy would be reduced. So, is it possible to switch between these 2 equilibrium states of the system? Yes, it should be possible, we think. Now, let's think about it in a more acceptable way. Let's say we have a power supply here. And this is a tabletop version which another student of mine, Emily Perttu, and I basically put together in an afternoon. This is not hard to make. So take a power supply, have a resistor and a spring. The top part of your capacitor plate is attached to the spring and is freely movable. And the bottom part, which we call the anvil, is at rest. And the electrostatic stress here can pull the hammer down to the anvil, discharge the capacitor, in which case the spring pulls it back. As it pulls it back, the capacitor can recharge based on the RC time constant of the circuit. And if one matches the RC time constant, the electric time constant of the circuit, to the mechanical time constant of the circuit, then one can create an electromechanical oscillator. A wristwatch is basically an electromechanical oscillator. So the question is, could one do the same thing here, where instead of having the battery, having a diode, in which case you would have a system which would discharge, recharge in a similar way, But now if you pull energy out of this system, you can play the first law against the second. If you extract energy from a system like this, you would be violating the second law of thermodynamics. So, can we build such a device? Okay, we have started building such devices. And this is a diode-driven oscillator, and this is a thermal capacitor which built out of silicon. Again, we have a N and P region, and so we have depletion regions here, in which case, based on Faraday's law, any loop has to have a zero net electric field integral around the loop. There should be an electric field down here. And in addition, we have cantilever springs here, basically thin pieces of silicon. So we have a spring, we have basic resistance, we can build resistance into the circuit, and we have our voltages. We've looked at this theoretically and looked at the operating criteria of it. There are three basic criteria to make an auto-resonant circuit using diodes, and this would be the following. Again, you'd have to have a mechanical and electrical time constant be roughly equivalent. And the spring constant, where the mass and the spring constant of the cantilever springs, this would be the time constant there, and RC would be the electrical time constant. The spring has to be sufficiently strong to overcome any van der Waals and electrostatic forces, basically stiction, such that once the two surfaces, hammer and anvil, come into contact, they will pull apart again. So this is an additional constraint. Spring force must be greater than stiction. And finally, if you're going to pull energy out of the system, the electric energy in this system had better be greater than the energy losses. And for us, we want to work in what's called a quality factor regime, much, much greater than 1, which means the system rings very well. Doing numerical simulations, we find there's a very broad parameter space in silicon devices which should allow this kind of device to operate. Now, let's look at power density. Dimensionally, power density, which is watts per cubic meter, should be equal to the electric field energy density, joules per cubic meter, times the fraction of the volume of the system of the entire device which holds the electric field. That will be less than 1, and the operating frequency of the oscillation. So the power density should scale as these three quantities as a product. If one looks at standard nano-electromechanical systems, NEMS devices, the electric field we'll be able to achieve in these devices will probably be roughly no larger than, in silicon, no larger than roughly the dielectric strength of silicon, or about 10 million, 20 million volts per meter. And the best we could probably hope for in terms of the fraction volume held by electric fields would be about 1% to 10%. And the highest operating frequencies that have yet been shown for NEMS oscillators is about 10 gigahertz. So, if one has an open cycle device, ones that export power, that means no feedstock to keep them warm, but simply turning heat into work and exporting the power, one could get power densities which are rather large, 10 to the 12th watts per cubic meter, but the whole thing would stop operating in about a millisecond because it would cool down so fast you would have carrier freeze out. The electrons would no longer be liberated into the lattice, and the holes would no longer be formed. The built-in potential would disappear, and the device would shut down. So if you export power from these devices, they can only do so for very small amounts of time. But on the other hand, if you were to add feedstock, in other words, keep them warm with air and water, to keep the energy flowing into them such that if you extract work from them, that new heat is being added to the system to be converted, then one could achieve probably 3 orders of magnitude less power density. On the other hand, if one had a closed cycle, in other words, you recycled the heat, had no feedstock, but simply used the heat to run your device, and once it was used and turned back into heat was recycled again into more work, then one could achieve very high power densities, where work and heat are simply being recycled one into the other. Practical example of this. Yes?
I didn't quite get that last one. Can you explain that one more time?
This is okay. Good. This is where things will probably start chafing at your thermodynamic conscience. And in this system, what you're basically doing is you are interconverting work into heat. And under these circumstances, when you take, let's say you have a chip, and you take some of that heat in the chip and turn it into electrical power, the chip will slightly cool as a result, because basically you've extracted the heat to turn it into work. Now when you use that heat to run a calculation, and then there's electrical resistance, it warms the chip back up, and then you reuse the heat again. So basically there is no heat change in the chip. All you're doing is changing its configuration. You're no longer bringing net energy into the chip. It's using its own thermal energy. Okay. So for a practical example, if you had a layer of these, of these small NEMS devices, cantilever devices, which let's say we're coupling their energy out as electricity using Faraday induction. A 1 centimeter by 1 centimeter chip, 10 microns deep, would be about 1 cubic millimeter of this material. At the maximum power densities, times this volume would tell you how much heat you could convert per unit time. This would be about a kilowatt, which is an extreme amount of power. The theoretical limit then, 1 watt of cooling would require about 1,000th of a cubic millimeter of SLDs. Now there are caveats here. Ultimately, you're probably going to be limited by thermal conductivity, how fast heat will move through your system, whether you're working in an open or closed cycle form. If you're exporting the energy out of the chip, it will freeze out eventually. Another way to look at power density is in terms of power per unit mass versus duration. And on here is the log scale of the power in watts per kilogram. And down here, duration of that power for each system in seconds. So for instance, if you take a 100 kiloton atomic weapon and detonate it, it will use up all its energy in roughly a microsecond, and therefore it will have extreme power per unit mass on the order of 10 to the 18th watts per kilogram for, let's say, a uranium device. High explosives would also be very high, but again, that would expend the energy very quickly. If you look at something like a space shuttle, it might burn for a few hundred seconds and have tremendous amounts of power during that time, so it has fairly high power densities. Jet engines and V8 diesel engines down here. Lithium-ion batteries, the best you could hope for would be down here, and I think that's a little bit high possibly. But the second law devices, depending on whether you operated in closed cycle or open cycle mode, could operate indefinitely at power densities somewhere between high explosives and jet engines probably. So very high power densities in principle. Now, this is where I want to clear out these some of the thermodynamic, how do I call it, adhesions. It took me years to actually come around to this way of thinking, because when you start looking at the second law being broken, you are looking through the looking glass backwards. Things that you thought were impossible are no longer impossible, and you have to reorient your thinking quite a bit. Thinking about thermodynamic efficiency now is meaningless, because you are always converting, the work you get always comes from heat, and as a result this ratio will always be 1. For a second law device, its thermodynamic efficiency is by definition 1, which is by itself a violation of the second law. You shouldn't be able to, for a heat engine, you shouldn't be able to break Carnot efficiency, which is always less than 1. A better figure of merit would be what kind of power density can you get versus the maximum theoretical power density. So that would be a better figure of merit, and that is yet to be determined. The second thing to realize when you look through this looking glass is this. Heat generation and cooling are the same thing. Normally you take work and you pay for this in the form of electrical energy or gasoline or whatever you want to use, uranium in a nuclear power plant. And through the second law, this low entropy energy gets converted to high entropy energy, which is basically heat, which is less useful. But with the second law devices, this would convert it back into low entropy energy and very usable work energy, which can be cycled again and again. So your power is basically the time rate of change of heat in the system. And if it's a closed cycle, there need be no change in temperature for your system at all. It simply cycles its energy from heat to work, back to heat, back to work, in a continuous cycle. You are changing the configuration of your system, but you're not actually heating it up or cooling it down. Power generation and heat extraction are basically interchangeable. Energy becomes recyclable then. This would be and this goes against every fiber of my body. In fact, my father, who was a physical chemist and brought me up in chemistry, I knew about entropy and the second law before I could play baseball. I didn't tell him about my research for 10 years because I knew he would be so deeply offended by it, being a physical chemist who live and die by the second law. But I could reach no other conclusion based on what the research shows. Other specifications for these devices. The operating temperatures for these proposed devices would basically be about 100 Kelvin would be the lower end. That's where you'd have carrier freeze out, and the built-in potential would disappear, and so would the effect. And maybe about 1,000 degrees at the top end, where your silicon begins to weaken. You have dopant diffusion. The intrinsic density of charged carriers gets so high that, again, your built-in potential disappears. There are theoretically no pressure limits for hermetically sealed devices. Size limits would probably be the lower limit, 10 to 100 nanometers. And you could extract the power in principle piezoelectrically by Faraday induction. And in the last 5 years, we have developed ways in which we can use these electric fields to drive chemical reactions in principle. So we carried out some laboratory experiments, and I'd like to discuss some of these experiments that were completed over the last 6 months or so. This is an electron micrograph of one of our devices. And if you want to see an actual one, I have one of our test chips up here if you wish to see it later. This is an SOI wafer, silicon on insulator. We have roughly a 2 micron thick layer of silicon on top of an oxide layer about a micron or so thick, and then about 400 microns of silicon beneath. And on the top, we carved it into various shapes. We were able to create, oh, enter? Okay, why don't you pass that around? Pull it out and open it up. Great. We made some p-in diode gaps, anywhere from 1/3 of a micron to 1.8 microns wide, so we could look at the electric fields that we proposed would exist within these p-in diode gaps to see whether they were really there. There were extreme doubts as to whether these would exist, because if they were, you would have thermal capacitors and the ability perhaps to violate the second law. So many people objected to our proposals up to this point because they said these couldn't be found. We also made some static cantilevers where we basically had cantilevers and hammers and anvils. And then we also made some dynamic cantilevers, ones we could actually move manually. This work was conducted at my university, Stanford, Standia, and out in the Netherlands. So here's an electron micrograph of one of the p-in diode gaps. N region, P region, separation in this case would be about 860 nanometers, oxide layer below in the handle wafer. So by way of just example, if one were to measure, let's say, 1 volt across from the N to the P region, dividing by this distance here, one would have an electric field of about 1,000,000 volts per meter. Here would be a diode cantilever. Again, here is the N and P region separated by a gap here. All of our experiments were done in air, so these are not vacuum gaps. They were done in air, but close to a vacuum. The measurements we made were with a scanning Kelvin probe microscope, which is a variation of what are called atomic force microscopes. And the way they work is this. If one has a surface one wishes to interrogate, one brings a very flexible cantilever with a very sharp tip. This tip can be only maybe 10 nanometers across at the tip. Bring it very close to a surface. Surface interactions between the tip and the surface will cause a deflection of a cantilever, which can be measured by bouncing a laser off the cantilever onto a photodiode. So very minute changes in the cantilever motion can be registered on the photodiode, going back to feedback circuits, and so on. So one can make very precise measurements of interactions between the cantilever and the surface, measure the surface roughness, surface potentials, and so on. So for our device, for instance, we would bring the probe tip maybe 10 or 20 or 30 nanometers over the surface and scan it over the N-type region, bring it down into the trench, back up over, and measure the potential difference between the P and the N region of the silicon. This would be scanned back and forth many times to build up a picture. Here is such a picture. This is an N and a P region. This is a regular p-in junction, solid, N and P, and here would be a trench, roughly 0.3 nanometers, 0.3 microns wide, which then was carved to fan out and become constant. These are 3 data sets averaged over these boxes, which measure the potential as one goes from the N to the P region. One finds that as one goes from the N to the P region, one sees a voltage drop, a voltage change. These voltage changes, these are different scales, voltage changes of roughly 100 to 150 millivolts. This is only about a sixth as large as the theoretical maximum for this doping, but that's probably because, and has been seen by other researchers, air and other contaminants will tend to wash out the electric fields a bit. If we had done this in vacuum, we would expect fields closer to a full volt. The artifacts here are based on the capacitance of the tip, and these can be subtracted. So the experimental results. For gap widths from 1/3 of a micron to about 1.8 microns, we found built-in voltages anywhere from 50 millivolts up to about 300 millivolts. These were all done in air. And gap electric fields on the order of 1,000,000 volts per meter. Had we reduced these distances by a factor of 10, in principle, we could have jacked these up by a factor of 10 as well. Dynamic cantilevers. For this system, we played a game, which was to force one of these surfaces into the other and see whether we could intensify the electric field and cause a formation of a depletion region here, pull this back apart, and see whether this would recharge. So here's the game. We've got a tungsten tip, a very small tungsten needle. On one of the outside movable cantilevers, which is going around the room right now, we were able to push the N-type material into the P-type material, the anvil. We had measured the electric field here previously. As we bring it down, we found in intensifying electric fields as we closed. When it was fully closed, we found that the electric fields broadened out across the entire region, forming a depletion region. And then as we let up on the pressure and pulled it back, the electric field would rebuild. I was able to do this 50 to 100 times. Bring it in, discharge it, pull it back, see it back and forth again and again. So the electric field so we found then for similar gap widths and electric fields, depletion region was formed and that it was reversed. We had a reversible charging and discharging of the electric field. So where does that leave us? Oops, back up for a second. Okay. We had completed a work cycle manually. We had started with an open gap, and as we closed the gap, we were able to find an increase in the electric field up to the point where we had touching between the N and P regions, in which case the electric field dropped as the depletion region formed. We let up on the pressure, and the gap opened again, the electric field, and we were able to carry this around through what is effectively a work cycle. We were able to infer electric fields for our gap widths with these voltages and these gap widths. The force, of course, is pressure times area. Electrostatic pressure is given by this. And so we completed a net work cycle. Those of you who have done thermodynamics know that the area within this then is a proxy for basically work done. If this is force and this is distance, then the force times distance is work. And so we were able to manually carry this device through a work cycle. Which raises the question, what if we had had thinner, more flexible cantilevers and we had mechanical, we had matched the mechanical time constants of these cantilevers to the electrical recharge time of this electric field. If we had given this a kickstart with the tungsten tip, then in principle the electrostatic pressure would have closed it automatically, discharged it, it would have been pulled back, and as it got pulled back it would have recharged eventually to resume its operation. If that had happened, that would have been a de facto violation of the second law. So what is that? Oh yeah, go ahead.
Sorry, can you back up 2 slides, please?
Yes.
I don't understand why the shape of when you open the gap isn't the same potential as when the gap's closing.
The electric, okay, so as the gap closes, the gap distance is decreasing.
Right. Potential goes up.
So it goes up. When it comes up here and the two are in contact with each other, then a depletion region forms.
It's when we move back and start to open the gap,
Okay.
how come you don't have the same potential you have when the gap was in that same distance when it's closing?
Okay. Okay, this is under the presumption this is open instantly, okay, in which it was not. Okay? So
Hysteresis, or is that just...
yeah, there'll be a hysteresis curve. So thank you for that caveat. I appreciate that. Okay. So the research status then is the following. We over the last 10 years we worked out analytic theory which shows that based on just the basic laws of physics aside from the second law, or even including it if you wish, you should have rechargeable diotic electric fields, and that you should be able to create MEMS and NEMS oscillators that employ them with very high power densities. We have done static numerical simulations using Silvaco codes, which confirm the existence, both the magnitude and location of these electric fields. Andrew not only carried these out, we had them carried out by Silvaco themselves and paid them to see if our results were simply a way we set up our codes. They found identical results. We have done dynamic numerical simulations and confirmed that these oscillators should be able to work over a broad parameter space. Linear electrostatic motors, rotary electrostatic motors, cantilever systems. These also have confirmed the analytic predictions of high power densities. We've now conducted laboratory experiments which have confirmed the existence of the electric fields. We have sent ships overseas to Westes in Netherlands, who have also used their new atomic force microscopes and have confirmed the existence and locations of these electric fields. We have confirmed the field discharge and recharge for manually closed cantilever gaps. So this brings us to the current experiments. We are currently running or setting up 2 experiments in parallel. The first is the MEMS-MEMS oscillator, which is basically the same kind of oscillator that we've talked about previously, but ones that are much more flexible. And we'll expect to finish these roughly in about 6 to 12 months. There's a second set of experiments which work with chemical detailed balance. And these are experiments which look at the dissociation rate of hydrogen on molybdenum and tungsten at high temperature, about 2,000 degrees. And we expect to complete these in about 3 or 6 months. These are based on some results over the last 10 years. Now, the MEMS and NEMS next generation device, it's going to be looking something like this. It's going to be about 3 centimeters long and about 1 centimeter wide. It'll have about 60 different experiments on it. And it'll be looking at the basic physics, auto-resonant cantilevers, and then there are some advanced designs on these chips as well. And the experimental goals will be to understand the auto-resonance process better from a basic physics point of view, diodic discharge and recharge speeds, look at durability and wear of the surfaces in contact, and then start playing around with power extraction, see if we can get Faraday induction to actually get power out. And also we're going to look at strict second law tests. Will these auto-resonant cantilevers actually work? Can we make a perpetual motion device? We also have some advanced designs, which will get around some of the limitations of the cantilevers. Now, the chemical experiments, I'm going to take a vote now. Does anyone want to hear about these or not? Any chemists in the room? Go ahead? Okay, I'll spend a minute or two on this. Okay. This chemical experiment, which we hope to complete in the next 3 to 6 months, I think is the most direct route to testing the second law, and if it's successful, would represent a true second law challenge, a true second law violation. But the problem is it's operating at such a high temperature that it probably wouldn't have any commercial value, unlike the silicon ones. But it would at least open the door if it worked. And this is based on experiments that I conducted 10 years ago, published here. And what it consists of is this: a vacuum vessel, basically at room temperature, in which one heats up a piece of a filament of molybdenum or tungsten, or both simultaneously, usually one at a time, and then backfill the vacuum chamber with a low pressure of hydrogen gas. Now, hydrogen can undergo various kinds of reactions on surfaces. When hydrogen molecules come to a surface, they can dissociate into atoms and then leave. Likewise, atoms can come to a surface and reform molecules and then leave. So you can have dissociation and recombination. Now, it is understood by the chemical community that at thermal equilibrium, the gas phase reaction of hydrogen molecules going to atoms has to be independent of surface composition. It must be. Because if it is not, if one had a closed black body cavity, a thermal equilibrium chamber, in which you had two surfaces that had different ratios of hydrogen atoms to molecules over them, they're disassociating at different rates, one could create pressure differentials or temperature differentials from which one could extract free energy. In fact, one could violate the second law. This would be a bona fide or de facto second law violation. So I carried out experiments 10 years ago to look at the dissociation rates of hydrogen into hydrogen atoms, and I found that they were in fact different. This is a plot of the power necessary to hold the filament temperatures up as a function at a given temperature at a fixed pressure of hydrogen, comparing molybdenum to tungsten. And what this is a proxy for is the dissociation rate of hydrogen into hydrogen molecules into hydrogen atoms. And I found that at low pressures, typically at a torr or less, at temperatures when one approaches about 2,000 degrees, one sees a separation of the behavior of the molybdenum versus the tungsten, which indicates that the dissociation rate on molybdenum is distinct from that of tungsten. Now, the reason why this did not constitute a second law violation is because this was not done at thermal equilibrium. The walls of the chamber were room temperature, whereas the filaments themselves were at 2,000 degrees. The experiments that we are now trying to create are ones in which we are creating small black body cavities, small regions, not much bigger than this, in which the filaments are again located of tungsten and molybdenum, held at 2,000 degrees, the entire system. If the difference in the dissociation rates of hydrogen, recombination rates of hydrogen, are different and maintained different like this at thermal equilibrium, then these pressure and temperature differentials are possible, and the second law will be de facto violated. Applications. Now, let's see what we can do with second law in terms of making computers. Now, we've already talked about this a little bit, but let's just kind of reiterate what we were talking about. Let's say we have a room like this, which has a temperature and lots of heat, oodles of heat here. One could, in principle, take some of this heat and, putting it through second law devices, turn it into work to run computers. Most of that energy would be converted back into heat, as a regular laptop does, which will go back into the room to be recycled. And then, if you're a good programmer, you'll get some useful information out of this by reconfiguring your computer. There is no net power consumption by this device, no net heating, therefore no cooling required. This is a device which, in principle, could perpetually compute with perfect cooling and efficiency 1. So there are 3 strategies for achieving this, which I'll call the heat recycler, direct drive, and thermal computing. Heat recycler. This one is the one that you would think of most readily, where you have a power source, typically maybe like a lithium-ion battery, provides work to your circuit, creates waste heat. Second law device is converted back into electricity, goes back into your battery, which is then recycled. This one has no heating. Direct drive. Why use a battery? Put second law devices directly on the chip. They create the electricity from the chip, drive the circuit, waste heat goes back into the second law device, and it simply feeds back and forth. Now you have no heating and no batteries. Second law devices could be centralized at the center of the chip, perhaps, or be distributed around the chip, like mitochondria in a cell. In the limit of this, why even have the circuit? Turn the second law devices themselves into the memory and logic elements, such that the cantilevers themselves, for instance, might operate as both the logic and memory elements, in which case the second law devices become these elements. How might you do this? Well, the architecture is well beyond this discussion, but here's maybe just a schematic of an idea. Let's say you had 2 cantilevers which were oscillating in phase with one another. That would constitute a 1. 2 oscillators oscillating out of phase with each other would constitute a 0. So simply changing their relative phase would constitute digital logic. Okay? Or I should say digital elements, and then you'd have to apply that to make your logic. Yes?
Wouldn't that imply relatively slow switching speeds?
It depends. I mean, you'd have, it depends how these calculations were carried out. The operating frequencies of these for MEMS devices at the top end right now is about 10 gigahertz. And if you had a lot of these on a circuit, on a board working in parallel, then you might be able to have very high clock rates.
How do you reverse the
Pardon me?
phase? How do you reverse the phase?
I'll leave that to the engineers. Okay? I'm just saying how schematically what it might represent. Okay. Okay, so are there any precedents for this? Well, for perpetual computing, no, but for cantilevers doing something of computer interest, yes. The IBM Millipede project, which has been going on for a decade or more, is a memory device which has a 64 by 64 grid of cantilevers on a very small area, which can read and write information on a plastic surface here with a theoretical storage capacity density of about 1 terabit per square inch, which is something like 4 times that of flash memory and about 100 times that of DRAM, I think, something like that. It's enormous. But what if you were to extend that idea and say, well, instead of just having these addressable cantilevers, have cantilevers which are auto-oscillating. And then you would control them somehow to carry out your calculations. In other words, you would have something like a whole bunch of these guys operating like a chip. And they would operate on their own heat perpetually, and your readout would simply be the configuration that your system's left in when you're done with the computation. Broader implications. Bless you. The reason why Jeffrey Wright and I started Paradigm Energy was not for computation per se, but because we know the importance of energy in the world. It makes the world go round in every sense. Rotationally, chemically, thermodynamically, ecologically, economically, geopolitically, militarily. Everything demands energy. It's the currency of change in the world. The current worldwide use is about 18 terawatts. To put that in perspective, 18 terawatts of power would be equivalent roughly to detonating a World War II type atomic bomb every 5 seconds in the world. That's how much energy is being used. Tremendous amounts. Depending on whom you ask, the energy increase in the next 20 years can be anywhere from 10 to 50%. 30% is greater than 30% seems to be the consensus in the next 20 years. And if you do a rough back of the envelope calculation, roughly 20% of the world's economy is devoted to energy. It's discovery, it's extraction, it's purification, it's transport, it's use, remediation, and everything else. It's a large fraction of the world's economy. It is considered perhaps one of the 3 most important resources of the 21st century. And what we hope to do is to forestall some of the downsides of it, which are a few of which are listed here. The one that concerns me the most is, of course, if you talk to a good fraction of biologists nowadays, they'll say we're in the middle of the 6th major mass extinction of the last 500 million years. A lot of that is being driven by energy concerns. So conclusions. The second law is absolute. Okay, I will say that straight out. It's absolute for now. Like any physical law, it is absolute until an exception is found to it. There are more than 25 theoretical challenges to it, and there are experiments in progress which hope to make these tangible. If any one of them succeeds, the second law will no longer be absolute. The power densities of most of them are minuscule. The ones for the silicon devices we're proposing are quite high. And these, if they are successful, would render very new technologies, applications, and industries. But all of this discussion, basically, for me, boils down to two questions. Can the second law be broken? And the second is, if so, will it be technologically and economically feasible to do so? This is a question that I cannot answer. This is the one that we are addressing in our research, but this will be left up to much larger concerns, bigger companies and larger research groups. Now, I have never made a prediction about the second law in public until now, but I will do it now. And I'll say this. I believe that the second law will be broken, probably experimentally within the next year, and it will take another year to get it published. And after that, it will take another 10 to 20, 40 years for that technology to be implemented if the answer to number 2 is yes. If the answer to number 1 is yes, can it be broken? It will change science, and that's fine. But if the answer to number 2 is yes, it will change just about everything. Any questions? Yeah.
When you start doing oscillation, what magnetic effects are you expecting to find?
What kind of magnetic effects?
If any.
Well, the devices themselves will not be magnetic unless we put a small magnetic domain to try to do some Faraday induction. But in terms of magnetic effects, if you have in the discharge region between the hammer and the anvil, when the charges annihilate, you might expect small currents, in which case you might use something like a Rogowski coil, some sort of induction coil, to measure a small magnetic field there. There might be a signature. Why do you ask? Is there
possible that might lead away some of the perpetual motion?
An energy loss that would keep.
I don't think so, as far as we know. You know, we looked at a number of different energy losses, radiative energy losses. We've accounted for local heating. We've accounted for the standard Qs of a semiconductor device. We've considered all of these things and have not found them to be significant. Yeah. Other questions? Yes. First name?
So when you're describing the device,
Yes.
at least from what I understood, you said you put the second law against the first law.
Yes.
Is it possible that, the first law has been patched up several times, so is it possible that even if the device works, second law is not broken, but first law has been patched again?
Okay, well that would involve a new energy source then. That would be nice. But if not, when I say play the first against the second, what I'm saying is this: if you extract work from the cantilever system, that energy has to come from somewhere. And if the system itself returns to equilibrium, that means it's in its original state, which means the energy has to have come from the heat bath. But the heat bath is not able to provide work. All it can provide is heat, which means that the work done by the cantilever had to come from heat from the heat bath in that full cycle, which by definition is the conversion of heat into work, which violates the Kelvin-Planck form of the second law. So I played the first law against the second that way. That might have been too fast, but it's in it. Okay, that's basically the argument. Yeah.
You're talking about the power densities of 10 to 12 watts per meter cube. What does that include? Is that just for across the junction, or across the gap, or does that include the entire?
That would include the entire device. Recall that the power density was a product of three things. It was the energy density in the electric field, the fraction of the device which is the electric field and not structural material, times the frequency. So I was assuming that the frequency was on the order of 10 to the 10th hertz. That's the upper limit frequency for NEMS oscillators right now. Roughly anywhere from 1 to 10% of the 1 to 10% of the device itself was electric field. The rest was silicon. So between 1% and 10%, yeah. And then finally, that the electric field would be on the order of 10 to the 7th volts per meter. So that was where the calculation came from. So you'd be lucky to get that. I mean, if you got within 3 orders of magnitude, you'd still be doing pretty well. Yeah, Rob.
So what is the breakthrough that you need to either prove that it's feasible or to it's a fundamental breakthrough that actually makes it feasible?
Okay, the two experiments which have been proposed, either of these would suffice. So if we could make a MEMS or NEMS oscillator which continued to oscillate on its own, in other words, we kickstart it, and then it continues to oscillate, and we were able to measure that periodic oscillation. By the fact that we've measured a periodic oscillation, we have extracted work from the system, and therefore that would constitute a second law violation. The other way to do it would be carrying out these hydrogen, molybdenum, tungsten experiments, again, in a black body cavity. And these would be much cheaper, much faster, but they wouldn't be necessarily economically feasible. They would not be integrable into silicon devices. I think one of the nice things about these silicon experiments is that they could be integrated nicely into existing chips, in a sense, if it turns out that you can extract energy from them. Yeah.
The fundamental energy source that you're talking about is not in a vacuum where energy is being spontaneously generated. It's essentially the sun and
Right.
the heat that's just latent heat in the environment.
That's right. We're basically using the resource of heat which exists everywhere. The amount of energy in this room is plenty to run all the lights, all the computers. It's about anything you could ever want in this room forever if you could recycle it. You could have a panel on the wall which is just a couple meters square, which would air condition your room, and at the same time run your TV set, your computer, your oven, and everything else, and all that waste heat would just go back in there to be recycled again. It's a completely backward way of thinking about things, and that's why people find it so objectionable. It goes against our experience, it goes against our thermodynamic training. But we're being led here because we're exploring parameter spaces now which are really inaccessible 100 years ago. And we have much finer ways of looking and building things now. And the second law appears to be ragged around the edges, and we're trying to exploit some of those loopholes. Yeah.
So your notion of the sort of completely closed system from which information pours out, but no energy is required, energy is not flowing into the system, seems to be in conflict with sort of Feynman's lower limits on the power consumption due to computation. Have you thought at all about those? Is that
those are based on the second law. Those are all
okay.
when you look at information theory, Landauer's principle and all these things, those are predicated on the second law. So you'd have to rethink information theory from the ground up. Yes, that's right. Good point.
So basically, the biggest open question now is what the physical size of the device is, like cantilever thickness and size.
Right. Well, you and Jeff and I worked out those parameter spaces, and they're broad enough that they can be accessed. But again, I mean, the second law is absolute for now until you can actually build a device that works. But we've seen the electric fields. We've seen them to be rechargeable. It's a matter of can we make a cantilever that can exploit those electrostatic pressures, cause a discharge, and then continue to run. If it does that, the second law is through. Yes.
What does the community of physicists think of this, or at least the ones that have written the paper?
The general population of physicists, it's a heresy. I mean, as you know, I mean that's a rhetorical question, really.
But the ones that don't say it's heresy, are they?
Well, okay, let's put it this way. This particular challenge has been up for 10 years. I mean, I've promoted it internationally over the last 10 years. There has been no resolution to it yet. No one's come up with a resolution that has stuck. And the biggest challenge against it was that we had no experimental results. Now we have them. I know of no theoretical objections to this thing working at this point, aside from the fact that it violates the second law.
It could mean that no one's actually looked into it and they've thought, it's heresy. It could mean they've looked into it.
That's correct. No, but nature is the ultimate arbiter. All I'm saying is that no person has found a fundamental flaw in it. We have not found a fundamental flaw in it. I have looked for one. I mean, honestly, I have. And we have carried out experiments which have not shown any showstoppers yet. So all I can say is there's something that if second law is true, there will be something in the way. And you, if you're a betting man, you would probably bet that way, and you probably would win. Maybe. I don't think you would, but I'm sure most people would say so. Yeah. Yeah, Andrew.
Did you guys observe any change on the surface after you did some of the manual charge and discharge?
On the devices I was doing, I was basically pushing the tungsten needle and doing it and basically closing it about 50 to 100 times. I didn't see any major changes during that time. But again, the surface wear is going to be a consideration. So we have developed new surface types, basically embedding nanotubes in surfaces, which will allow you to have a discharge with basically no wear. So that's another aspect of the company was to develop technology for reducing surface wear, because that is an issue, certainly. But I don't know if I answered your question right.
I was just wondering what everyone else thought about it, but I was just wondering what everyone else thought about it. But,
Well, there haven't been, I mean, basically, the scientific community tends to ignore things for the most part. It'll ignore things as long as possible. So that's fine.
Yeah. I mean, you didn't answer it, but it looks like it's unanswerable at this point. So
Yeah,
my question is,
the ultimate arbiter of truth in science is experiment. not
yeah,
theory.
right, yeah.
That's
But
correct.
we'll have to wait for the experiments, and that means I want to know the answer to the question now. So.
I don't know the answer to the question. All I'm saying,
Sounds
that's why I'm doing the experiment.
Yeah.
I mean, I'm an experimental physicist.
But you can never really prove the positive case, you can only disprove it, right?
That is the key. That's the wisest thing said this afternoon. Okay, that's the case. You can never prove the second law is absolute, but you can prove it is not, if you can find an experiment that falsifies it. That's Popper's basic thesis of falsifiability of scientific theory. That's right. And so it is what it is. I mean, we are trying the best we can. Okay. Yes.
Do you have any idea why, what's the scale factor or energy factor that is now allowing us to see evidence that might not be true? The second law. In the very beginning, you drew the diagram of
Yes.
where you used to only be able to experiment in this window, and
Right.
now we're out here.
Right.
Why might we only be able to see evidence of second law being true outside of a certain
I don't know why you would say why. I would say that we have macroscopic devices, macroscopic behaviors like ourselves or automobiles or anything like that. The second law appears to work there.
well, like with relativity, you can look at the equation and say, well, if the factors are like this, there would be no difference.
Okay. So let me put this thing into a more philosophical perspective. All of the challenges that have been proposed, that have been worked on at USD, can fall into a single rubric, if that's what you want, as an explanation. That's this. Most of thermodynamics and the second law are presumed to be true in what's called the thermodynamic limit, which means a system which is infinitely large, has an infinite number of particles, but the density is basically the same throughout. It ignores boundaries. Okay? It ignores discontinuities in a system. For instance, when you have an N and P-type piece of silicon, when you put them together, you have a discontinuity in the behaviors of these two materials, and when you put them together, that's when you get a voltage. The chemical potential difference turns into an electrostatic potential difference.
So the macroscopic world doesn't have this kind of discontinuities?
The discontinuities over such as the gradients and potentials resulting from these discontinuities are so small that they're usually ignored. I mean, they're micron size in the case of a silicon device. But if you build devices down to that scale, then they start becoming important. After all, the electric fields only become sizable when you get the gaps down to about 1/10 of a micron. Then they become sizable enough that they start making a difference. But you would never see them at a macroscopic scale, even if they exist. They would be so washed out, or so insignificant compared to other free energy sources that you wouldn't see much of them. You wouldn't care much about them. The world is driven by free energy. We have plenty of free energy, from the sun, from food, and all this. But it's not always enough for things like running computer chips. And it just so happens that this silicon technology may have the ability to violate the second law at these distance scales where it can be very handy. Yes?
Question about when the actual physics of the device.
I'm sorry.
I have a question about the actual physics of the device
Yes.
itself. When the hammer hits the anvil,
Yes.
that's when electrons jump across from
You have annihilation.
the p-type.
Electron and Holton annihilation.
And that's when the hammer cools down because the hot electrons are crossing the gap, right?
I don't know if it's cooling down or not. You'd have recombination there.
Yeah, recombination, but where is the heat being turned? So my question is, where is the energy coming from? And it seems to me, I was talking to Andrew about this, that when the hammer hits the anvil, you have the hot electrons, they've got enough energy to jump across and recombine.
Okay, now these aren't hot electrons. These are electrons which are on the surface. These are
Surface electrons with enough kinetic energy, right?
No, they don't have to have kinetic energy. They're basically attracted electrostatically to the holes.
Okay, so they just simply have to be on the surface.
Yeah, they will be on the surface. You'll find you'll find that basically it's like a capacitor plates where all the charges are on the surface of the capacitor plates.
Right. Though from what I understood about how it worked, that cooled the thing down.
I don't think so.
Okay. So where's the heat coming into the system from the outside to, So the heat, so you've got like a bath, a heat bath,
Right.
and the heat is coming into the system somehow, and then that's turning into work somehow. So
Okay.
which part of the system
Right. Okay.
is cooling down?
If the system actually, if you don't have a drag on the system, in other words, if you're not trying to extract heat from the system, simply let it run on its own, basically idle, it doesn't heat up and it doesn't cool down.
Right.
There is no net heating or cooling of the system. Okay. So the deeper question is when you start extracting heat from the system. Start extracting energy from the system. How does the heat flow back into the cantilever devices? Right. Yeah, we've tried to do. We have pestered everybody that we can about dynamic simulations on this, and nobody can do the dynamic simulations. That simple cantilever device is beyond simulation ability. Okay. Current steady state. So we have thought about it. We don't know exactly. We don't have an analytic theory for it, and there are no numerical simulations that can handle it. And if you know of anyone who does that, we'd be very interested. We've looked for 10 years, and no one can simulate this because too many things are happening. You have diffusion going on, you have charge creation and annihilation going on, you have flexure of the springs, all sorts of things are happening. It's a very complex system. You look at it closely.
The graph with the going through the work cycle that compromises the.
We're not looking at microscopic behavior there. That's correct.
Right.
That's right.
So that's what leads you on to think that this will work. That whatever.
Yeah. Basically, we looked at the system from a thermodynamic point of view and found that if this thing electromechanically oscillates, then there's something wrong with thermodynamics. And so we're using thermodynamics against itself in a sense. Okay, looking for internal consistency.
Part of what he was asking is when the charge carriers jump across the gap and annihilate, how do they show back up on the other side?
Okay. Yeah. I can sit down and go through the process with you if you want, but if you can look at it in terms of electric fields, driving currents through. It'll take a little bit of time. I don't want to do it here on the floor because it takes so long, but I have worked that out. That has been worked out.
Is there a higher level, sort of intuitive thermal flow explanation for this? That isn't the details?
Thermal flow.
I'm just talking about the. Yeah.
I think that the charge carriers will be delivered from the valence band to the conduction band by absorbing heat.
Okay.
Yeah, that's correct. But I was talking about the whole device. Yeah.
It's the heat that actually pops the electrons or the holes up to the conduction band where they can actually move around.
Because you have to have a thermal path just like you have to have an electrical path.
Yeah.
Right.
So that's where it's sucking the heat out of the system in a sense.
Thank you for coming. Okay. Well, thank you very much. And let's chat afterwards. Okay.